So, good morning everybody. I have to say I caught quite a cold and I'm not really at the height of my limited abilities, and I'm sorry for that. But I'm not sure how digestible the lecture will be today. All right, apologies in advance. In any case, what did we do last time? We looked at two things. Number one, how do magnetic fields evolve under plasma flows? Number two, how do magnetic fields act back on the plasma flows themselves? And we first laid out a number of assumptions under which we wanted to address these questions. And these assumptions were that the plasma is dominated by magnetic but not by electric fields, and that the charge density times the speed of light can be neglected compared with the current density. All right, and under these assumptions and the additional assumption that the plasma moves slowly, we derived first of all an induction equation that looked nice at first sight but was homogeneous in the magnetic field and therefore cannot explain how magnetic fields can be formed. It does explain how magnetic fields evolve. It does not explain where they originate from. And therefore we repeated this derivation of a similar equation again, taking into account that the plasma consists of at least two components. And then we saw, all right, we can augment the induction equation for the magnetic field by a term that is non-zero if we have flows under baroclinic conditions. So when the gradient of the pressure is not aligned with the gradient of the density. All right, and then we saw if we return to the hydrodynamical equations and ask what effects do magnetic fields have on them, then we saw, well, they do obviously not have an effect on the continuity equation because they do not interfere with the conservation of mass. But we obtain an additional force term of the magnetic field back on the plasma flow. And this force term had two interesting components. The first one was there is a force coming from a gradient in the magnetic field squared. That's the energy density of the magnetic field, or equivalently the pressure of the magnetic field. And so we acquire an additional term that adds the magnetic pressure to the thermal pressure. That was the first term that we additionally get in the Euler equation, and the second term had to do with the fact that magnetic fields want to be straight. It was a term that was proportional to B times the gradient applied to B, so that is the derivative of the magnetic field along the magnetic field. And of course this force contribution is the stronger, the more curved the magnetic field lines are. Okay, then we had a brief interlude about additional terms in the energy conservation equation. All right, something that I missed last time and that I wanted to at least mention is that we had a systematic procedure in hydrodynamics how we could add further contributions to the hydrodynamic equations. And if you remember, the hydrodynamical equations are just conservation equations, so they can be expressed by the vanishing divergence of a tensor. And you can get the exact same terms that we dealt with last time if you add to this tensor the energy momentum tensor of the magnetic field, and then apply the divergence and you get the exact same terms, right? So you can also approach the entire line of derivation that we had last time in the same systematic way that we used in hydrodynamics, just by adding a vanishing tensor divergence, in this case the vanishing divergence of the energy momentum tensor of the electromagnetic field. which in this case, of course, is only a magnetic field. All right, so far so good. And then we did something else that is important to me, namely, we compared the two terms on the right-hand side of the induction equation. And there's a diffusion term that is proportional to the Laplacian of the magnetic field. And there is an advection term that is proportional to the curl of V cross B. It's the advection term that tells you how the plasma flow is carrying the magnetic field around. And the other term shows you how the magnetic field can diffuse away in the plasma. And the prefactor of the diffusion term is c squared over 4 pi sigma. C squared over 4 pi, the conductivity of the plasma. So the higher the conductivity is, the less important is this diffusion term. And this is what people mean if they say that in an ideally conducting plasma, the magnetic field is frozen in and it can't move relative to the plasma. And so wherever the plasma goes, the magnetic field also has to go. Unless the conductivity is finite, and then you have a diffusion term. And what was important to me last time was the direct comparison that we had between the induction equation and the vorticity equation. And the vorticity, the curl of the velocity field in hydrodynamics, obeys the exact same dynamical equation as the magnetic field. It contains a diffusion term and it contains an advection term. And the diffusion term in the case of hydrodynamics, in the case of the vorticity, is just given by the viscosity of the fluid in this case. So I wanted to draw these parallels. And then if you take the ratio between the two, the ratio between the advection term and the diffusion term, in both cases you get a Reynolds number. A magnetic Reynolds number that tells you how ideally conducting the plasma is, and a hydrodynamical Reynolds number which tells you how important viscosity is. And the higher the Reynolds number, the less important is viscosity, just by the definition of the Reynolds number. All right, this was the program for last time. Do you have questions? Not the case. Then, here is what I wanted to continue with. So we discussed the generation of magnetic fields as the last thing last time. And now I would like to jump over ambipolar diffusion. This is something we may or may not talk about as we move along, depending on how much time will be left. But now I wanted to go to waves in magnetized cold plasmas. And waves means electromagnetic waves. So again, we are going to look at dielectric response, in this case of magnetized plasma. And I'm doing this first of all for the fun of it, right? Because now we do have the situation in which the plasma itself has its own ideas about preferred directions. This is the situation that we so far did not have. Now there is a magnetic field in the plasma, therefore there is a preferred direction in the plasma. And then of course, the way how electromagnetic waves can propagate in the plasma must depend on how they propagate relative to the orientation of the magnetic field. And this gives rise to a really awful complication. Namely, if now you have a magnetized plasma and an electromagnetic wave coming in, then you have two directions. And you have a direction of the wave vector of the infalling electromagnetic wave, and you have another direction, which is the orientation of the magnetic field. And then, of course, depending on how they are oriented relative to each other, all kinds of things can happen. This is what I wanted to discuss today. Now, if we assume a thermal plasma, or if we assumed a thermal plasma, like we did in the case of a non-magnetized plasma, then the analysis would be much more complicated than I would like to present in a lecture. And therefore, we are going to assume that the plasma is really cold, right? That the only motion of the plasma electrons is due to the infalling electromagnetic field, plus the magnetic field that the plasma has on its own. Okay, so we are going to neglect thermal motion. All right, that's the program for today, I hope. All right, so we are dealing with waves in magnetized cold plasmas. So now I'm going to write down an equation of motion for the plasma electrons. And of course you know what that is, right? The acceleration of a plasma electron will be given by the Lorentz force. All right, so this will be minus E over m. Let me just write m for the electron mass. There will be no other mass. There will be no other mass today. Okay, then we have an electric field. The electric field is not something that sits in the plasma, but this is something that we radiate into the plasma. Okay, so this is something fundamentally different from the magnetic field that is now going to appear in the rest of the Lorentz force equation. So these are really fundamentally different things now. This is the magnetic field in the plasma plus the magnetic field of the infalling radiation. This is the electric field only of the infalling radiation. But then V over C is a small number. We're aiming at linear response. So we need to neglect terms of higher than first order in perturbations. The velocity divided by the speed of light is a perturbation because it's in our case only caused by the infalling electromagnetic field. Right? We said we are going to neglect thermal motion. All right, so this is already a small number, therefore in the magnetic field I'm going to neglect the magnetic part of the infalling radiation. So therefore I signal this by writing B0. Right? B0 is the magnetic field that lives in the plasma. E is the electric field that migrates into it. All right. Now E will be harmonic. Right? This will be an infalling. No, this will be something that we can decompose into plane waves. So I'm going to do that. And if I do that, then of course the response of the plasma, namely the velocity, will also react in a plane wave form. And therefore, if I then decompose the velocity field and the electric field here into plane waves and apply the time derivative, this will lead to a minus I omega. If omega is the frequency of the infalling electric field. So I'm writing minus I omega V. Time derivative has changed to an algebraic operation. And again, I'm using the same symbol for the amplitude of the plane waves as I used for the complete velocity field. I don't think that this will give rise to complications. All right, then on the right-hand side, E over m times E, okay, fine. And now let's have a look at this term here. Because I want to write it in the form like matrix times velocity. Now, how do I do that? I take the amplitude of the magnetic field, not its direction, the amplitude, divided by mc. I'm factoring this out because, as you may remember, that's the Larmor frequency. And that's the frequency dictated by the gyration of an electron in the magnetic field B0. All right, so I can identify the Larmor frequency omega L here. And now I need to take account of V cross the unit vector B hat in the direction of the magnetic field. Now let me write this term here explicitly in a different this is a vector. If I take the I component of this vector here, the I component of the vector v cross b hat, this is epsilon I j k b hat k times vj. And now I'm going to collect these terms here into a matrix curly B. Okay? This is antisymmetric, of course. It looks funny, but it will be very convenient in everything we do now. Okay. So I can write the whole equation as minus E over M times E, and I can change the sign, I can change the sign on both sides of the equation because all signs are negative. So then I have omega L, the Larmor frequency, curly B matrix times the vector V. All right, and now the same game starts as always. Right? First of all, I can now combine these two matrices here. Sorry, these two terms that are proportional to V. I'm introducing a unit matrix here to replace the V by unit matrix times V, and I'm subtracting omega L times the curly B matrix times V equals E over M times E. Okay, so we have a matrix on the left-hand side. Let's call it M. And if you want to know how with what velocity the electrons respond to the incoming electric field or electromagnetic field, in the magnetized plasma, we would just have to write V equals E over M, inverse of that matrix, times E. Okay, we will need to check that this matrix is invertible, so we will have to see when its determinant is going to vanish, and so on and so forth. But now we have the electron velocity in response to the electric field. And now we play the exact same game as we did with the thermal, but non-magnetized plasma. Now I'm going to say, if I know the electron velocity, then I know the polarized current density in the plasma. All right. How do I get this? This is going to be minus E n times V. Right, every electron has a charge of minus E, their number density is small n, their velocity is V. So I can simply write this is minus E n E square. Right, I need to multiply this minus E n with E over M here. So I'm getting this prefactor. Then the matrix M to the minus 1 and the electric field. But once I know the polarized current density, I do know the time derivative of the polarization. Right? This was one of the starting points that we had in this part of the lecture. Right? The time derivative of the polarization. This is the polarized current density, and so therefore I can use this now. I can use that J pol is already decomposed into plane waves, as I decompose the electric field into plane waves. Then the response, the polarization, because it's a linear response, will also be in plane waves. Right? The polarization P will then also consist of plane waves, and therefore the time derivative will be minus I omega times P. All right. same notational sloppiness. P is now the amplitude of the plane waves and not the complete polarization anymore. Nonetheless, on the right-hand side we have E square n divided by m, matrix m to the power of -1 times E. All right, remember we did exactly the same thing for a thermal plasma. Right? We went through the polarized current density, except that in the case of a thermal plasma, we said, all right, I will have to integrate over the perturbation in the phase space density of the electrons. I will have to integrate over the volume, sorry, the momentum space volume. This is now the polarized fluctuation of the electron number density. And if I multiply this with -E and I multiply with the electron velocity, this was the term that we used in case of a thermal plasma. And then we went exactly the same steps further on. Right? We used this equation to find the polarization. And once we have the polarization, we can say, okay, the dielectric displacement, d, this is E plus 4 pi p by definition. The 4 pi, of course, is an artifact of Gaussian units, Gaussian CGS units. And at the same time, we know this will be epsilon times E. And this will allow us to identify the epsilon. All right. So again, I'm introducing a unit matrix here to represent the E. And now I'm going to use this equation here. So from here we have P is E square n divided by I omega m, m to the -1 E. I need to multiply this with 4 pi. And I will pull the imaginary unit into the numerator, which will change the sign. So this will be -I times. Now, 4 pi n E squared divided by m. Do you recognize this? That's the plasma frequency squared. Lovely. It reappears here. Okay, then we have 1 over omega. I need to take this into account from here. M to the -1 times E, where now the E multiplies both terms here. Okay, so this is the plasma frequency squared. And we have a relatively simple or intuitive way of writing the dielectric response tensor. Namely, from the comparison of this side with the rest, you would read off epsilon is unit matrix minus I times, let me write omega p squared divided by omega m to the power of -1. This is, of course, the main difficulty now. And with that, we do already have the dielectric response tensor for a cold magnetized plasma. And now, of course, we need to make sure that we find out what m to the -1 is. If you do that, don't even think of using Cramer's rule. You can do so much easier. And this is also something that I wanted to show you today. We want to know what m to the -1 is, given that m is this matrix over here. All right, so we have m is I omega unit matrix minus omega L times B. And I want to know what m to the power of -1 is. Now, I'm going to make an ansatz for that, which will make this calculation much, much, much more simple than just inverting this equation, this matrix blindly. from all the material that we have in our plasma, we can form three matrices. The unit matrix, the matrix B vector B hat vector B hat. Right? That's the matrix that, let me write this down. So this we always have. Then this is a matrix that I can use, right? Because I know that the direction of the plasma will have to play some role. Sorry, the direction of the magnetic field. And I have a third matrix here, which is the curly B. And now I'm trying, as an ansatz for m to the minus 1, a linear combination of these three matrices, because the matrix m to the minus 1 has no other choice than to consist of these three components. And there cannot be anything else in it. All right, so let us use the ansatz some function a that we need to find out times the unit matrix plus b times the magnetic field matrix plus c times the curly B matrix here. All right, that's the ansatz that we make. And now, of course, I need to make sure that m to the minus 1 times m is the unit matrix, and I need to find A, B, and C such that this relation is satisfied. Okay, so we have A times the unit matrix plus B times B tensor B plus C times curly B times I omega, the unit matrix, minus omega L times B. Okay, now in order to simplify this a bit, this has to be the unit matrix. In order to simplify this a bit, let me calculate the square of the curly B matrix separately, because that's the only one that's going to be complicated. And remember, the curly B is a vector product. So the curly B square is the square of a vector product. This leads directly to the Grassmann identity, expressed in matrix form. That is it. If you want, you can work this out, but you will use the Grassmann identity in order to work this out. So there is nothing new in that. Right? So, of course, you get this by decomposing this with a Levi-Civita symbol and so on. But that is the result. Try it out, right? If you have some time over Christmas. All right. Another thing I need to use here is that the product of this here with B is going to be 0. And this is because of the symmetry of the B hat, vector B hat, or tensor B hat, and the antisymmetry of the curly B. All right, so if I take this into account, then what do I get? I get an I omega A times the unit matrix. But I will get further terms that add to the unit matrix. Nonetheless, I omega A times the unit matrix, that's that. Then I have A times minus omega L times B, because the unit matrix times B is, of course, B, the curly B. So minus omega L times B times the curly B. Okay, next one will give me an I omega B from here times this matrix here times the unit matrix. The next one will drop out because of this. B tensor B times curly B is 0. So then we only have plus I omega C, capital C, times the curly B matrix. And finally, we have minus omega L capital C. Now B square, but B square was this. All right, and the result of this calculation must be the unit matrix. And now, of course, we get three prefactors to three matrices. Let me first collect the terms that are multiplied with the unit matrix. So I omega A from here plus omega L times C times the unit matrix. Now we have terms proportional to B tensor B. So this will be I omega B from here and minus omega L times C from behind. So that's that. And then we will, yeah. Are you here or there? Above. Do you mean this equation? All right. We got that. We got that. No, we did not get that. That's what you meant? Thank you. Fortunately, I didn't get that far so far. All right. Finally, we have plus I omega C, that is proportional to the curly B, and we have minus omega L times A must be the unit matrix. So, of course, now we need to have the prefactor of the unit matrix equal to 1. So we have I omega A plus omega L C equal to 1. And we need to have the other prefactors to be 0. So I omega B minus omega L C equals 0, and I omega C minus omega L times A also equals 0. If that is the case, then we can satisfy our inversion equation, and we are done. And then we have inverted our matrix here. Now I'm going to multiply this. I'm going to multiply this by what? Let's take omega L. So I'm going to multiply this by omega L and have I omega L times A plus omega L squared times C equals omega L. Okay, and I'm going to multiply this one by I omega. Okay? Then I get minus I omega L times A minus omega squared times C equals 0. Okay, and now I just need to add these equations, and I get omega L squared minus omega squared times C equals omega L, or C equals omega L divided by omega L squared minus omega squared. Okay, good. We have the first. Now we take the second. From the third of these equations here, we can directly conclude that A equals I omega divided by omega L times C. But for certain reasons, I want to express everything by A, not by C, so I'm inverting this and say C is minus I omega L divided by omega times A. I'm going to use this later. And if I insert the result that I already have for C, then this is I omega divided by omega L squared minus omega squared. Okay. Now I use this to get B. So the B is minus I omega L divided by omega times C. Well, I would have to divide by I, but this means I might have to multiply by minus I. And now if I insert this result here for C, I get a minus I squared, that's minus 1. I get an omega L divided by omega squared times A. Okay? So this means now that I can relatively easily write down what the matrix M is, or rather M to the minus 1. I can factor out A from all contributions. So then I start with the unit matrix within parentheses. Then the B term is just minus omega L squared divided by omega squared. So minus omega L squared divided by omega squared times A times B tends to B. And the final term is minus I omega L divided by omega times A. So then I have the curly B matrix here. All right, that's our inverse matrix. If you want, try it out, right? M to the minus 1 times A must be 1, but this is how we constructed it. So maybe you trust this. But now, let us have a look at the determinant of M. Because with the determinant of M, we can simplify things quite a lot. So that's the determinant of I omega unit matrix, where is M? Minus omega L times B. Okay, I'm factoring the I omega out. Then I'm left with unit matrix plus omega L divided by omega, plus I times B. Okay. Now I have to do with the determinant of a 3 by 3 matrix. So this means if I factor a common factor out, the result will be proportional to that prefactor to the third power. So that's going to be I omega to the third power. And now the determinant of the rest, unit matrix plus I omega L divided by omega times B. Okay, now, if you have a matrix of this sort, and this is quite a general expression here, right? Because it just contains the Kronecker delta. But if you want to calculate a determinant like that, you can convince yourself that this is just 1 plus A squared. Isn't this beautiful? Try it out. All right. So then the complete result is I omega to the third power. 1 plus this prefactor I omega divided by I omega L divided by omega squared. So that's minus omega L squared divided by omega squared. That's our complete determinant. You shouldn't just believe this. You should try this out. Okay. Now I can obviously pull the factor of omega squared into these brackets here. And I get I cubed, so that's minus I, times the remaining prefactor omega, and then omega squared minus omega L squared. Okay, so this means that omega squared minus omega L squared is just the determinant of sorry, the determinant of m divided by minus I omega, so this is I determinant of m divided by omega, and therefore I can write the prefactor a, or the function a that we had over there, as minus I omega, and now the inverse of that. So omega divided by I did m, and this is minus omega squared divided by the determinant of m. Okay, so let me now, with that, minus, is that correct? I need omega L square minus omega square over here. So that's the negative of the inverse of that one. So I need to multiply this result by minus this. Well, that should be correct. Okay, now let me use this result for A and finally write down the matrix M as minus 1 over determinant of M. Now I'm going to pull the omega square in, and I get omega squared times the unit matrix minus omega L squared times B tends to B minus I omega L times curly B. I find this quite instructive because you have a Larmor frequency for each B field factor. And if you have two of these factors, then you get an omega L squared. If you have one B field factor, such as in here, you get just one Larmor frequency here. And notice we have an I in there, right? There's an imaginary unit remaining in there, which will give rise to funny things. All right, so let me now pull things together. And right underneath the dielectric response tensor here, unit matrix minus I omega p squared divided by omega, and now the complete inverse M matrix, which has a minus sign, so this is plus divided by the determinant of M, and now omega squared times 1 minus omega L squared B times B minus I omega L curly B. And we have our dielectric response tensor. Okay. So that's the main result of the first part of the lecture today. And then I suggest we have a break and I wipe the board, and then we continue with that. Let me save the determinant also. Minus I omega. Okay. 5 minutes break. Are you ready to move on? So we have a beautiful expression here. I was just asked, why is this different from what you find in the theoretical astrophysics book? There you find something different. There I introduced an abbreviation, WL, as omega L divided by omega, just as a shorthand notation. But I can do this in print, right? I can never do this on the board without confusing you all the time, right? Because then you cannot distinguish between what is WL and what is omega L, and this is all very dissatisfactory and so on. But if you want to compare two results that you find in this theoretical astrophysics book, this is the reason. Same thing for omega P and WP, right? WP would be omega P divided by omega. Reading this again, I didn't think that this was particularly well chosen, but okay. I heard the statement yesterday from a famous physicist who said it's never too late to decide not to write a textbook. I should have considered this earlier. All right, now we are going to play games. I'm now going to project the epsilon tensor on pi parallel. And pi parallel, I mean, is this. Right? It's the parallel projector on the magnetic field. And of course, we will also have a perpendicular projector, 1 minus b times b. Okay, of course, I want to split this horrible function up into palatable terms, right? So yes, if you multiply this with a parallel projector, you get the parallel projector here. If you take its trace, you get 1. So it's not the end yet. So then you have this whole prefactor here. Omega p divided by omega dot m. Times omega squared. And now again, the trace of the parallel projector, which is still 1. Now, we arrive at this term here, which gives you a minus I omega p squared omega L squared divided by omega dot m. Now we have the parallel projector times itself. Right, here's the parallel projector again. And so we have the square of the parallel projector, but since the parallel projector is a projector in the first place, it squares to itself, and the trace is still 1. Okay, and since the parallel projector is symmetric and the B is antisymmetric, the curly B projects out. Okay, so we have these terms here. Now let me summarize them a bit. We will have 1 plus I omega p squared divided by that m. That's the common, these are the common factors of both terms that follow. Then we have an omega minus omega L squared divided by omega. Okay, right, I'm combining these terms. Now let me pull 1 omega out. So this is 1 plus I omega p squared divided by that m, omega times omega squared minus omega L squared. Do you recognize this? Omega times omega squared minus omega L squared. So this I times omega squared minus omega L squared is just minus the determinant. And it goes away. And I'm sorry. This is what I should have done, right? So in order to repeat what I just said, right? This I times omega times the term in parentheses is just a negative determinant. And what is left over is 1 minus omega p squared divided by omega squared. Okay, beautiful. Do you remember that waves, longitudinal waves, can propagate when the longitudinal dielectric function is 0? They can propagate if they have the plasma frequency. You can read this immediately from here, right? Okay. Now we need the perpendicular or the transverse dielectric functions. And here I need to take into account that the perpendicular projector projects on a two-dimensional subspace, and therefore we have to take a factor of a half into account. Now we have the perpendicular projector times E, times epsilon, sorry. This will be epsilon perpendicular, or epsilon transverse. All right. If I apply the perpendicular projector to the unit matrix, take the trace, I get 2, divide by 2, I get 1. As it has to be, right? We have to compare the vacuum. Next thing, plus I omega p squared divided by omega 1 over that m, omega squared. Now again, we have the perpendicular projector applied to the unit matrix, blah, 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 blah. So here we get a factor of 1. Then we have minus I omega p squared divided by omega times omega L squared divided by the determinant of m. We're getting all these factors right. Okay, and now I have the perpendicular projector applied to the parallel projector. All right. And now what follows would be, or would involve the following calculation. We need the trace of unit matrix minus B times B applied to the curly B. So here you need the trace of this antisymmetric matrix here, which is 0, and here you need the trace of the symmetric matrix B tensor B times curly B, which is also 0. Right? So this is just 0 and we are done. Okay. And so we can continue writing. How do I do that? Number 1. I'm just going to insert this expression over here for the determinant. This changes the sign, this cancels the I, this cancels the omega, and what remains is just omega p squared divided by omega squared minus omega L squared. That's it. Okay. Now we have our parallel and transverse dielectric response functions. But we have to care about a third function now, which is neither parallel nor transverse. And it's the rest that multiplies the curly b over here. So now let me just combine all the terms that are proportional to the curly b. That's the common prefactor, and then we have minus I omega omega L. And then the curly b. Okay. Now I insert again the definition or the result for the determinant. So this is minus I squared, that goes away. Then we have omega p squared. The omega cancels. Omega L. These are all the terms in the numerator, and the omega goes away, divided by the determinant of m. So this is minus I omega squared minus omega L squared. The minus I in the denominator is a plus I in the numerator, so I have plus I omega p squared omega L divided by omega squared minus omega L squared. Okay, so this is the prefactor of the matrix G in the dielectric response tensor, the matrix B, sorry. And I abbreviate this as I times G. Right, so I introduce a third function, G equals omega p squared omega L divided by omega squared minus omega L squared. And this we have in addition to our two dielectric response functions that we know from before. Right? And the reason is only that the magnetic field that is in the plasma gives the plasma a certain direction. Right? And then terms appear that are no longer either longitudinal or transverse, but can be both. Okay, so with these functions, we can write the dielectric response tensor as epsilon equals unit matrix. No, sorry, we have taken this into account. Epsilon parallel times pi parallel plus epsilon perpendicular times pi perpendicular plus I G curly b. Okay. But notice how we got this pi parallel and this pi perpendicular here. These are projectors relative to the magnetic field. This is something different than we did before, where we had projectors relative to the k vector of the incoming electromagnetic field. So what we are looking at now is longitudinal or perpendicular polarization of the electric field with respect to the magnetic field in the plasma. This is not longitudinal to itself or transverse to itself. This is important if we now move on, because now that we know the dielectric response tensor, of course we have to return to our propagation condition for electromagnetic waves. And what was that again? We had the condition that 1 minus k times k minus omega squared divided by c squared k squared times epsilon applied to the electric field must be 0. Do you remember that? We had derived from the Maxwell equations this propagation condition here, or this matrix equation, for the propagation of electromagnetic waves. And now you see, this is now also a perpendicular projector, but on a different axis. And this gives rise now to a really, really huge mess of different complications. Right? Because depending on how K and B are oriented with respect to each other, electric fields or electromagnetic fields will propagate or not, or you will convert transverse to longitudinal and back and whatnot. Right? Okay. So in order to see what that what that tells you, you need to see you need to set the determinant of that matrix to 0 in order to see where this equation can have non-trivial solutions in the first place. Well, okay. And this is now something we have to deal with. So how do we go about this? Of course, now we need to insert this expression here for the dielectric response tensor and move on, right? But we can achieve this in the best way if we choose one of the vectors k or b in such a way that either k or b looks into one preferred coordinate direction. Well, we can work out the determinant in any coordinate frame you like. So let us choose a particular one and see what we can do about this. Because the way how it's now written is really a bit complicated. So there's a systematic way of converting these projectors into each other. So what I'm now going to do is to express the transverse projector on the k direction, right, on the propagation direction of the electromagnetic field, in terms of the other two, right, the projectors relative to the magnetic field. Now, how do you do that? You do it exactly as if you wanted to express a vector with respect to a different basis. Right? You would say, okay, I make the ansatz that this perpendicular projector that I need is some linear combination. Let me use the capital A again because we don't need it anymore from previously, times pi parallel plus b times pi perpendicular, where the pi's without a tilde are the projectors relative to the magnetic field, and the pi with the tilde is the projector relative to the propagation direction of the electromagnetic wave. Now, A is the trace of pi parallel times pi tilde perpendicular. And I use the scalar product that we introduced for matrices, which is this expression here, and then I get the coefficient A out. Okay, now let's do that slowly. So we have a parallel projector relative to the B field. That's that. We have a perpendicular projector relative to the K direction. So we have that. And now what happens is that, of course, when we multiply this matrix product out before we take the trace, first of all we get B tensor B, and then we have minus this matrix here, right? B tensor P times K tensor K. So by the rules of matrix multiplication, this is going to be B tensor K times the scalar product of B times K. Okay? Now, these are two unit vectors, so I can express the result as a cosine of an angle. And I call this mu. And this will be later just the cosine of the polar angle of our spherical polar coordinate system. And later we are going to orient either K or B into the z direction. And then the mu will just be the polar angle of the other vector with respect to that one. All right, but if you now take the trace of this is 1, right? Because just the scalar product of B with itself, B hat with itself. And now we get another scalar product here by the trace of B hat times K hat. So this is just going to be 1 minus mu squared. Or sine squared theta, if you like, right? And the B is going to be a half times the trace pi perpendicular times pi tilde perpendicular. So what is that? This is 1/2 times the trace, 1 minus B tensor B times 1 minus K tensor K. Okay, that's going to be a half of the trace of 1 minus B tensor B minus K tensor K. And then again we have B tensor B times K tensor K. So that's going to be mu plus mu times B tensor K. Okay, now if you take the trace, this gives you 3. This subtracts 1. This subtracts another 1. So this will be 1. And if you take the trace of that, that's going to be mu square. So this is going to be 1 plus mu square over 2. Or 1 plus cosine theta squared over 2. Okay. But this means that we can go on writing here in expressing the perpendicular projector with respect to the K direction. We can write 1 minus mu squared times the perpendicular projector, sorry, the parallel projector. Now plus 1 plus mu squared over 2 times pi perpendicular. All right, now we can express everything with respect to the B field. Of course, we could have done otherwise, right? We could have represented the complete dielectric tensor with respect to the K field, to the K direction. In a way much similar to that. Now, if I now take this determinant equation that we had upstairs here, then I need to make sure that the determinant of the perpendicular projector with respect to K, so this is 1 minus mu squared pi parallel plus 1 plus mu squared over 2 pi perpendicular minus omega squared divided by c squared k squared. This expression is a w squared in the book. Omega squared divided by c squared k squared. And now we have epsilon parallel, pi parallel plus epsilon perpendicular, pi perpendicular plus ig b. Okay, that's the determinant we have to calculate. And as you will see, this is relatively easy. Because now we are going to say B hat is 0, 0, 1 or EZ. And I'm going to turn the coordinate system such that it's going to be locally aligned with the B field direction. If this is the case, then the parallel projector is just going to be this spectacular matrix here. And the perpendicular projector is going to be this matrix here. Now, what is curly B? Okay. Of course, all the diagonal elements are going to vanish. Of course, it will be antisymmetric. So all we need to calculate are three things. If I go to the 1, 2 element of B, this will be epsilon 1, 2 something times B something, and something can only be 3. Right? So this is going to be B3 hat. 1, 3, then the remaining component must be 2, but then you have switched the order, so this is minus B2 hat. And of course there's just one left, right? 2, 3, 1, then they are in natural order and you have B1 here. Okay, it's going to be antisymmetric, so we have minus B3 hat, B2 hat, minus B1 hat. But in our case, B hat has just one component, right? And this is B3 and this is 1. So the whole curly B looks like 0, 1, 0, minus 1, 0, 0, 0, 0, 0. Okay, this will turn out to be relatively manageable. So, let us have a look, because I want to start at the top left, let us have a look at pi perpendicular first. Here's a term, and here's a term that contribute. So, I'm defining a function small a that's going to be 1 plus mu squared divided by 2 minus omega squared divided by c squared k squared times epsilon perpendicular. This will be the function that multiplies the perpendicular projector, and this will therefore appear at the top left and at the center position of the diagonal here. That's the function a. Okay, now, from the parallel projector, I will get the diagonal element matrix 3, 3. So now I'm going to collect all the terms that multiply the parallel projector. That's 1 minus mu squared minus omega squared divided by c squared k squared times epsilon parallel. And that's it. Okay. And then naturally I would have a function c, but c is reserved for the speed of light. So let's call it d. This will be the amplitude multiplying the matrix B, the curly B here. So this will go into the 1, 2 or the 2, 1 components. And we are going to have just one expression here, namely minus omega squared divided by c squared k squared times g, and we will have an additional factor of I that I don't write down now. Okay, so with these definitions, the complete matrix for this particular orientation of the B field or of the coordinate system relative to the B field, we can write A on the diagonal and here, and B down here. This is how we constructed them, right, from the perpendicular and the parallel projectors. And then from the matrix curly B, we will get the 1, 2 and the 2, 1 components. And these will be I times D. And minus ID here, and zeros elsewhere. Well, this is a matrix whose determinant we can calculate, right? Okay, so the determinant of this is going to be B times A square minus D square, right? So I can swap lines twice and columns twice, then I have just the prefactor B, then I have the submatrix of these two, that's A square, minus I square D square. And this gives a minus D square here. So this must be 0, right? So either B is 0 or A is plus or minus D. Hallelujah. So B is 0 or A is plus or minus D. These are our propagation conditions now. Now let's see. Either B is 0. So if this is to be 0 here, then we have C square K square times 1 minus mu squared equals omega squared times epsilon parallel. Okay, so I'm taking this expression for B, I'm multiplying with C squared K square, I'm setting the result to 0. And if I now insert the epsilon parallel, it's still above, so that would be 1 minus omega p squared divided by omega squared. And so you find the relation C square K square 1 minus mu square equals omega square minus omega p squared. This is the dispersion relation. This is one of the dispersion relations we get from this equation here. Okay, so that's one possible wave mode that we got from B equals 0 alone. The other one is going to be a little more complicated. This is dangerous. And this is pretty, isn't it? All right. I still need these functions, obviously, right? So I can't wipe them off. So okay, now let's have a look at the other dispersion relation. A is plus or minus D. Okay. A. 1 plus mu squared over 2 minus omega squared c squared k squared, oh dear, times epsilon perpendicular, so times 1 minus omega p squared divided by omega squared minus omega L squared. This is A. If I just resolve the different symbols we have introduced. Okay, and this must be plus or minus D. What is D? Minus, well, since we have plus and minus, I don't have to take care of the sign, so we have omega squared divided by c squared k squared, and now times G. What is G? G is this one. Omega p squared omega L divided by omega squared minus omega L squared. So that's our dispersion relation for the other mode. Let's see what we can do about this. So first of all, we multiply this by c squared k squared. Then we have 1 plus mu squared over 2 c squared k squared. Okay, fine. Then we can multiply the omega square into this and get omega square minus omega p square omega square divided by omega square minus omega L squared. Okay. I multiply with c square k square, so this is gone. So I have equals plus or minus omega p square omega L divided by omega square minus omega L square. Okay, now obviously I can still combine terms to make things simpler. I should have factored omega square out, but okay. So I have 1 plus mu square divided by 2 c square k square equals, now I'm going to collect everything on the other side, and I'm going to factor out again an omega square. That was not good to do that. So we have 1 minus omega p square divided by omega square minus omega L square. That's from here. And the minus sign is taken care of by the prefactor. And then we have plus or minus omega p square omega L divided by omega square minus omega L. But this can now be massively simplified if you combine the final two terms. Right? You bring them on the same denominator. So you see this is 1 minus. Then you have a common prefactor of omega p. Then you have omega plus or minus omega L divided by omega square minus omega L square times omega. Now whatever you do, one of these factors is going to cancel, right? Because, sorry, this omega square minus omega L square is just omega plus omega L times omega minus omega L. So irrelevant of or irrespective of what sign you have here, one of these factors is going to cancel. So this is going to be omega squared 1 minus omega p square divided by omega plus or minus omega L. But that's how that looks manageable. That looks manageable. And now we do have two dispersion relations. I'm going to copy this one again, c square k square 1 minus mu squared equals omega squared minus omega p squared. So what could you do with that? You could calculate phase velocities, you could calculate group velocities, effective speeds of light, and so on and so forth. Right? And we have, let's make it as similar as possible, c square k square 1 plus mu square divided by 2 equals omega squared minus omega omega p squared divided by omega plus or minus omega L. These are the two dispersion relations. Okay, what you see here is that first of all, properties like group or phase velocities will depend on how the electromagnetic field will be oriented with respect to the magnetic field. So here is a 1 minus mu square. The mu is the cosine of the angle between the unit vector in k direction, the unit vector in b direction. So this is a sine square theta. So suppose the magnetic field is aligned with a k vector, or differently, the electromagnetic radiation falls into the plasma along the direction of the magnetic field. Then mu is plus or minus 1, this is 0. Then you see immediately omega square must be omega p square, so omega must be omega p. This is only possible if the wave has the plasma frequency. If, however, there's a misalignment, then of course you have a finite factor and the frequency will shift away from the plasma frequency. Same down here, but there is a plus or minus sign here, and that adds or subtracts the Larmor frequency. And this is the most interesting part here, because that tells you that, we will see this next time, that you have two propagation speeds for two polarization modes. Right? If you calculate a group velocity here by taking d omega dk, you will see, okay, you will find two group velocities. In other words, there will be two speeds of light. Okay? And this means that two polarization directions of the electric field will propagate at different speeds. As we will see next time, these are circular polarization modes. Now you can think of a linearly polarized electric field as being superposed of phase-aligned circular polarization modes. But now in the plasma, one of them goes faster than the other. And then the linear polarization direction is going to turn. So whenever electromagnetic radiation travels through a magnetic field, you will turn the polarization direction, and this will be frequency dependent. So now suppose you look at the polarization map of something, you don't see the polarization that there actually is. You see the polarization direction as it comes out of all the plasma distributions that you find on the way. This effect is called Faraday rotation. It depends on 1 over omega square. We will work this out. Sorry, we will work this out next time. But this is one example for deceptive effects that intervening plasmas have on propagation direction, and the derivation of the result for the Faraday rotation next time. This was the main motivation for doing all that. Right? Just to see, okay, how do polarization directions change by propagating through a magnetized plasma? Okay, so next time we will return to that, to these two dispersion relations here, and discuss them a bit. What we will also see will be the following. Suppose you start with the decomposition of the electric field into a longitudinal and a transverse component. Aha. Suppose you do that. It's gone, unfortunately. But that this determinant should vanish is a consequence of the fact that we need to multiply this matrix here with the electric field, right, in order to get a solution for the electric field. But in particular, this term here, this antisymmetric part, in most cases makes sure that a longitudinal wave does not stay longitudinal, and that a transverse wave does not stay transverse. So usually you will enter the magnetic field with a proper vacuum transverse electromagnetic wave. Then it runs into the plasma. Its two circular polarization modes are propagating at different speeds. It will acquire a longitudinal component because there's no other choice, right? Because this matrix here will mix longitudinal and transverse modes. So it will acquire a longitudinal mode of oscillation in addition to its transverse mode of oscillation. And the longitudinal mode is going to be damped, right? Because there is an I in here, right? So we have, again, an imaginary part of the dielectric function, and so on and so forth, right? So there will be constant change of longitudinal and transverse orientations. The magnetic plasma or magnetized plasma by this dispersion relation here, because of the plus and minus, turns out to be birefringent. It has two different indices of refraction for different polarization modes, and so on and so forth. And so the phenomenology that we now get is very, very rich, and of course we will only touch on part of that. Okay, and if you really want to know what happens, you will have to solve the matrix equation for the electric field, and then see from the dispersion relations what possible relations exist between frequency and wave vector or frequency and wavelength. All right, that's what I wanted to do today. So since we have Wednesday today, we're going to meet Monday next week. And this will still not be the last time before Christmas, right? Because the Christmas break starts on Thursday next week. So we will have a full week next week. All right, then see you next Monday.